Alright, hello and welcome back. My name is Cameron Kirk and this is another video on my series of videos for the DE10-Nano Projects. And in this video, this is actually going to be sort of a follow-up to the previous video where we went over the my first SoC Simple Hardware Adder project, which is where we saw how to connect a hardware adder on our FPGA and control it from a C program in the user space of our Debian SD card image on the DE10-Nano. And in this video, what I'd like to do is talk a little bit about the code. I didn't go over it in the last one because I just sort of like copied and pasted the code in and compiled it, put it on the board, and we saw that it worked. And that's because I actually have some thoughts on this code that I thought it was worth putting it in a separate video to go more in depth on it. So I'm going to open up Visual Studio Code here. I'm in our folder from the last video, the Simple Adder Live. And let me get out of the way here. So, and then let's increase the font size a couple notches. Let's go one more. Okay, so here's our code, and basically what we're doing here is we're getting the bridge address and how long our bridge is. That's all fine. Really, what I want to talk about is this project's decision to track individual pointers to these different registers or different operands of our full adder. So basically, if we take a look at what we did in QSys, right here, we have our PIO out, and our PIO in, and they're all back to back to back. We saw in the last video basically the very next memory address of this memory map device will be at offset 10, hex 10. And that's just picking up right where this last one left off. And same thing with 7, then we're going to pick it right up again on 8. So basically, if I were to make a picture, I'm going to use Excel because I think Excel is really good at showing this. If I were to make a picture of what our memory looks like, we have 0, 0, 0, 1, 2, 3, 4. Let's see, can I change this to hexadecimal? I don't think so. Give me 1 second here. I'm going to pause the recording. Okay, we're back, and what I've done here is I've basically put the memory addresses in column A here. So if we take a look, we're going from 0 to 7, and then from 8 to F, and from 10 to 17, but I didn't bother with putting anything past 10. And then we know that our PIO is a 64-bit value, and the first one, so let me just mark with an X the first one. Okay, so these are these addresses in the memory are for our first PIO device. And we know that it is 64 bits, and if we use the calculator here, and I'm assuming our system, I'm pretty sure our system is byte addressable, so 64 divided by 8, 8 bits in a byte, so there's 64 bits, for every 8 bits that's a byte. I was making sure my math checked out. That should be 8 bytes, and we have 1, 2, 3, 4, 5, 6, 7, 8 bytes. So this value here, this is our, whoops. This is our A operand. And I'm guessing that this is our most significant bit. I might have this backwards. Why do I keep doing that? Oh, I know why. I need to fix that. Okay. So you might start to see what I'm getting at. Okay, so there's A, and then this is where B starts, and B goes all the way to F. So here's B. And then the sum goes at this memory location below. And I'm not going to actually label them all. Right, so this is our whole slice of memory. And what our code, or the provided code, is basically doing is we are getting a pointer that points to this memory location in memory, including the offset and everything according to what the kernel tells us. This is the pointer to use to get to the memory that you used in the mmap call. So just to make sure it's clear what I'm talking about, right here we get our bridge map as a pointer, and then we're using whatever that pointer's value is and adding our adder A, which is our preprocessor definition of the base address. So we're using this offset to step from the bridge whatever the kernel returned to us, and we're stepping up to get a pointer to A. So we're getting a pointer to A, and then we're getting a pointer to B, and then we're getting a pointer to the sum individually. And instead what we can do is we can use a struct. So instead of tracking, doing the arithmetic and adding to get our pointers and hoping that all works out well, it's actually a really common thing to, especially when you have things that are back-to-back in memory. If you apply a struct, you're basically doing what I just did here in Excel, which is labeling all of these guys A, and then immediately what follows is my variable B, and then immediately what follows after that is the next variable. So let's jump over to our code, and we are going to define a struct, and I'm going to call it adder, and we are going to have, well, we're going to have a semicolon at the end here. And this adder struct has three things in it. So just like we did here, these are basically the three things that are going to be in our adder. So in our program, in our C code, we're allocating three separate variables to track the values, and then we're allocating three pointers here. And the choice to use an unsigned integer 8, you're saying this pointer points to an unsigned integer of 8 bits. But really, I mean, technically it should be a void pointer, because you're not pointing to a unsigned integer of 8 bits. If you want to keep it generic, do a void, or it should be a 64-bit pointer. But it really doesn't matter. Like this isn't like a promise or anything that this pointer really does point to this data type. But what we're going to do is we're going to get rid of these pointers. We're not going to track it all manually anymore. And we're going to move these guys into our struct. Okay, and then basically what we're going to do is when we get our return from the kernel, we're going to use that memory location that the kernel gave us, and we're going to map it onto our struct. So basically this struct will kind of be like an overlay that like lays out these are these sections, and then you can reference variable names with it. So I'll show you what that looks like right now. So we're not going to initialize things in the struct. We're just saying the struct looks like this, and what this is saying is that in memory, the first 64 bits, or the first 8 bytes, are for variable A, and then immediately the next byte is for B, and then immediately after that is for sum, just like what we have here. And this works. I have seen, well, no, we're good. So the next thing we're going to do is our bridge map. This is actually going to be, instead of a unsigned integer 64, so a pointer that points to a type unsigned integer, it's actually going to point to a struct data structure of type adder. So this is going to point to our adder struct. So we're saying whatever is in this pointer it's pointing to a this kind of structure, which is 3 variables. Okay, and from here, we are going to change this in a second, but we need to change this one. So no longer is mmap returning a pointer that we're going to cast to a pointer that points to an unsigned integer of 8 bits. It is actually going to point to a struct adder structure. So we're saying whatever comes out of this pointer, this is called casting, this is called typecasting, and basically we're saying whatever you get out of here, pretend it's this. Treat the data like it's this. And so we're going to treat whatever's coming out of here like it is a pointer to a struct. And we're going to set our bridge map equal to that. Okay, and so now down here, this is where the magic happens. We no longer have to do our pointer arithmetic and make those individual pointers. We don't have to do that anymore because we're working with all of our variables in a struct, and we know that we have contiguous memory for each of our operands. And this is horrible, horrible code. I saw somewhere on a Stack Overflow post, I wish I could find it again, but I did a little searching and I can't find it in my history. It was from like last month or something. But basically it was saying like, pretty much don't write code like this. You should really use a struct. It's much better. So what this is basically they're saying whatever's in this pointer, cast it to a unsigned integer 64-bit pointer, and then dereference that pointer. And then when we say dereference, we're saying take whatever is at that memory location, the value there, and set it equal to A. And so we're assigning this memory location the value of A. What would have been much better, let me move these guys down. So this code here, this is just parsing our argv and argc. This is something we're not going to discuss in this video. It's pretty straightforward C programming. But what this is essentially doing is it's taking what we parsed out and setting it to those memory locations. What would be better is if we would say bridge map, which is a struct pointer, and we're going to dereference. I believe this is one way of dereferencing, but I prefer to access arrays because my brain processes that better. So basically we're saying like, you know, you could put, like, let's say you have an array of structs, which would look like, you know, you have your memory looking like this, and then immediately after the sum operand ends, another one starts. So immediately following that, it would be here, and this would be like index 1, and this is what's at index 0. So that's another way of dereferencing a pointer. But yeah, so I'm saying take the first index, index 0 of our struct, so the first occurrence of our struct, and keep in mind our memory doesn't actually have another struct that follows, so this syntax might be a little bit misleading. Other programmers might look at this and go, oh, maybe I can put a 1 there, but no, we don't have that memory. You can only put 0 here. So just keep that in mind. But if you set it up that way, you could have a subsequent struct. But anyways, we're going to use the dot operator and access A from our struct. And we are going to assign it this value here. And we really don't need to have a placeholder variable. And we just did the equivalent of that. So now we'll need to do the same thing again for our value of B. And again, hopefully this is making sense. I'm doing the best I can to explain what's happening here, including with these visualizations here of how we're basically overlaying our memory with names using a struct, because that's what structs are for. And then lastly, we're not going to use this pointer stuff. We're just going to use our bridge map struct pointer, and we're going to access sum. Just like that. Let's see, did I do that right? Oh, you know what, even better. Rather than having this, middleman variable, we don't even really need the middleman variable. We can just print out what's that sum. Just like that. And I believe that is all we need to do for these changes. And this just sort of makes our code much more compact. I don't think it completely tidies up everything that this code is doing, but it definitely it's definitely an improvement. It's a lot easier to understand what's happening, and it's leveraging structs, which I think, and we don't need these offsets anymore. There's no point to tracking that. Okay, so yeah, let's compile this, and I mean, we're pretty much going to see that the same thing happens. Okay, let's see. Oh, I think I forgot to remove one line of code. Just get that out of there, save. Okay, so I'm going to cross-compile this, and it's done, and I'm going to push the up arrow to recall my scp command. Oh! Let's go to the tabletop. Oh, my camera. Give me 1 second here. Okay, we are back, and it would help if my camera was actually plugged in, if I wanted to use it. So I'm going to plug in the USB UART here, and I don't know why I always like this demonstration, but I'll go ahead and do it anyways. I'm going to open up a program like Putty, and switch it to, switch it to serial mode. Baud rate is 115200, and I know it's going to be on COM3, but if you're not sure, you can go to Device Manager, and it will tell you under the ports. Oh, let me get out of the way. There it is. COM3. It's COM3 every time. I've seen it change after restarting it a few times. Okay, I'm going to open up that COM port. I'm also going to change the screen size, or sorry, the font size to 14. Click OK, apply. All right, and I am now going to supply power to the board. And we start receiving output. You know, the board comes to life on this terminal here over the USB wire. Okay, I'm going to log in. I'm going to run ifconfig 192.168. Okay, and then so our IP address is right there. I'm going to do a clear. I'm going to do a ls-al, and here is our old myprog live from August 2nd at 1:17. I'm going to transfer the new one, our newly compiled one. And now when we run this ls, we can see August 3rd. And then, let's see, /myprog live 100, 110, yeah, 100, 200, 300. So the code still works. And, you know, there's not really... yeah, I don't think there's really going to be much. Well, actually, yes, I could argue there is a huge performance boost from doing this. We've basically made the C program run more efficiently by making these changes. And, you know, if you're going to go through the trouble of having a FPGA with your custom Avalon memory mapped peripheral full adder on your FPGA, and you're going to access it from a C code, you probably should be careful about what sort of computation you're making your C program do, because you might be giving up some performance by doing some unnecessary work with pointers when you can just use a struct, because the operands are in contiguous memory, and that's what structs are for. Anyways, I hope I explained all of this clearly enough. I think I started to ramble a little bit there. But yes, structs are a really powerful technique of like, basically you lay out the format of the memory, and you can mix and match types too. It doesn't have to be it doesn't have to be the same type for a struct. You can put whatever you like for the struct, and then when you get a pointer, you can just say, okay, this pointer is going to be a struct pointer, and then boom, like your struct pointer can be used like a struct, and you can dereference the pointer and start getting access to the struct, and you can be a lot more efficient. Anyways, thank you so much for watching. I hope you found value from this video, and I will see you in the next one. Take care. Bye-bye.